Hey everybody, we are going to be doing a mini lab at home today. And the result of this mini lab, you're going to come up with an efficiency calculation that we're going to share with some partners when we come back to school on our next in-person day. So we've been learning about a bunch of different types of energy. We started by learning about kinetic energy and gravitational potential energy, and then we went into learning about spring energy with elastic potential energy. Now we're going to add thermal energy to the mix. So thermal energy, sometimes we call this heat. We denote the letter Q for this type of energy. And the equation right here on the board just says Q equals mc delta T. Okay, the letter Q means heat. It's the type of energy itself. The M is mass. The C is something called specific heat capacity, and delta T stands for a change of temperature. Now, the specific heat capacity for different substances is always unique to that substance. I have the specific heat capacity for water, which is 4,186 joules per kilogram degree Celsius. But the one we're going to be looking at today is going to be our turkey. We're going to do an experiment called How Not to Cook a Turkey, which is then also going to go along with one of your practice problems that you'll work on right afterwards. Okay, so the turkey that we're actually going to look at today is kind of a funny little thought here, but the turkey itself is actually just metal. And let me just show you the situation that we're dealing with here. So what I have here is this container, and it's just like an insulated tube. And in the tube is a bunch of metal beads, okay? And the beads themselves are just little steel balls. And I've got a thermometer coming out of here. And I'm just gonna go ahead and put them back in the insulated container. And what we're gonna do is we're gonna be doing some work against gravity. And we're gonna be storing gravitational potential energy. And then I'm gonna put these beads up at a high place. Then they're gonna fall. And that conversion from gravitational potential will turn it into heat energy, or Q. And then we're going to look at how efficient the process of me turning this is. Okay, so that's our basic idea. So the initial type of energy that we're dealing with today, right here, the gravitational potential energy, EP, grav, is equal to mgh. Sorry, fix that. It is equal to mgh. And the type of energy that that is going to turn into, the final type of energy, is Q, or heat, and equals mc delta T. Okay. Now, the specific heat capacity for our turkey, which really is just steel, it's actually written on the board there for you. It's 449 joules per kilogram degree Celsius. You can see that's significantly less than water. Steel actually doesn't take a lot of energy to heat it up compared to water. Water actually takes a lot more energy to get its temperature to change. Now, the mass of the steel in here is 491 grams. I'm just going to go ahead and put that on the board here. So the mass is 491 grams, or 0.491 kilograms. All right, now the delta H, the height that we're going to be dropping this from, is going to be the length of this tube. So I'm just going to go ahead and measure the length of the tube. We get it all set here. And this tube is 0.82 meters. And I'm going to go ahead and just put that up for you guys. 0.82 meters. And we're also going to do 50 turns to equal the number of meters that I'm going to drop it from in total. Okay. All right, now the next thing I want to do is find out, well, what's the temperature change going to be? And that's going to relate to the starting temperature. And so the starting temperature, actually it's right over here, is on the board right now. And you can see it's 22 degrees Celsius. All right, so I'm going to go back to my board. I'm going to put on 22 degrees Celsius. Let's add that on there for you guys. Whoops, let me get that there. Okay, so the starting temperature, temperature initial, equals 22 degrees Celsius. All right, now let's go ahead and do it. I'm going to do 50 turns, and we're going to see what the temperature goes up to. So let's go ahead and start that in the view. So, and I'll put this screen up for you too. Okay, so I'm going to go ahead and collect this information. All right, now I'll start here, and I'm going to turn it one full turn. 1, 2, 3, 4, 5, 10, 20, 30, 40, 47, 48, 49, 50. Okay, 50 turns. And I can see that the beads heated up. And guess what? I actually heated up too. Doing work causes me to get warmer also. Okay, so let's go ahead and take a look at our delta temperature now. So I'm going to go ahead and stop the data gathering. And let's auto scale so we could see the change. And you can definitely see the change of temperature going on right here. It made it up to 22.8 degrees during that time. Okay, so going back to our original data, the final temperature was 22.8 degrees Celsius. So that gives us a delta temperature of 0.8 degrees Celsius. Okay, and given that we had 50 turns times 0.82 equals 41 meters. So I'm going to go ahead and put that on there for us also. Okay, now notice our data. So this is where you're going to do the calculations now. But the initial energy type was MGH. The final energy type was MCAT. You've got all of your data here. You've got mass. You know what gravity is. You have got delta 8, height is 41 meters. You've got the Q equals MCAT. You've got M, again. You've got C, which is 449 joules per kilogram degrees Celsius. And you have delta T of 0.8. So what I want you guys to do is go ahead and calculate your gravitational potential energy, calculate your increase of Q for the turkey based on the equations, and now your efficiency is your energy output over your energy input as an absolute value times 100. And in this case, your energy output is going to be your gravitational potential energy. So that would be, see that erases, there we go. Now the output in this case is going to be actually your temperature, that's what I should have said. And your input of energy was MGH. Okay, so go ahead and do your calculation, find out what your efficiency was, and we're going to compare that with our groups next class. Okay, now last thing I'd like to mention here before we go, that this little mini lab, you want to have it in your journal so we can talk about it next class. And then the thermal energy problems that you're going to work on today, question number 1 is just like this kind of a problem here. So think it through and answer that one before our next class too. So that's it today, guys. Good to see everybody through this remote world right here. You guys have a really good day and enjoy yourself. Bye.